Hi, I am Ravikumar. I would like to explain the working of the IGBT. The IGBT is the insulated gate bipolar transistor. The IGBT has three terminals, namely gate, collector, and emitter. Collector is also known as drain, and emitter is also known as source. In a p-channel IGBT, the direction of the arrowhead would be reversed. The symbol of IGBT as shown in figure below. This is the basic structure of IGBT. The main difference between the structure of the MOSFET and IGBT is the existence of the P plus injection layer, which forms the collection of a IGBT. IGBT structure contains a PN thyristor structure between the collector and emitter terminals. The N plus buffer layer between the P plus drain contact and the N minus drift layer is not essential for the operation of the IGBT. IGBT with buffer layer are termed as punch-through IGBT, whereas IGBT without buffer layer are termed as non-punch-through IGBT. As explained here. The classification of IGBT. The classification IGBTs are symmetric IGBTs and asymmetric IGBTs. The symmetric IGBTs are non-punch-through IGBTs and asymmetric IGBTs are punch-through IGBTs. This is the figure of symmetric IGBTs. This is a forward blocking IGBT and this is a reverse blocking IGBT. These are the main differences. The source is reversed. In the non-punch-through IGBT, the N plus buffer layer is absent in the structure. N plus buffer layer is absent in the structure. In the forward blocking mode, the collector is positive with respect to the emitter. Therefore, junction J1 and J3 forward bias, junction J1 and J3 are forward bias, and J2 is reverse biased, and hence decide the blocking capability of the device. Junction J2 is formed between a moderately doped P layer and lightly doped N minus layer. P layer and N minus layer. Hence, the forward blocking capability is decided by the N minus drift layer. From reverse blocking IGBT, when a reverse voltage is applied between the collector and the emitter, junction J2 is forward biased and junction J1 and J3 are reverse biased. Junction J1 and J3 are reverse biased and J2 is forward biased, and hence the reverse blocking capability is decided by them. Junction J1 has the heavily doped source N plus layer on one side and the moderately doped P layer on the other side. Hence, it does not have the capability of blocking voltage. Junction J3 will block all the reverse voltage due to the presence of highly doped N minus drift layer on its one side. Therefore, the reverse blocking voltage of the non-punch-through structure will be comparable to the forward blocking voltage. Therefore, the non-punch-through IGBT has a symmetrical blocking capability. They can be used in rectifier circuit. The symmetric IGBTs are used in rectifier circuits. From the asymmetric IGBTs as shown in figure, the figure A is a forward blocking IGBT and a reverse blocking IGBT is in figure B. Here also the main difference is the source is reversed and N and buffer layer is present here. Punch-through IGBT consists of N plus buffer layer between the collector P plus junction layer and the drift layer. When forward voltage is applied, junction J1 and J3 are forward biased and J2 is reverse biased. As discussed in the case of NPT, the forward blocking capacity is decided by the junction J2, and here also the thickness of the drift layer will decide the forward blocking capability. from the reverse blocking voltage from the reverse blocking IGBT. When a reverse voltage is applied between the collector and emitter terminal, junction J2 is forward biased and junction J1 and J3 are reverse biased and will have to block the reverse voltage. But as explained earlier, J1 cannot block layer reverse voltages, and now due to the presence of heavily doped N plus buffer layer on one side of J3, junction J3 also cannot block a large reverse voltage. Therefore, the device will break down for reverse voltages. Punch-through structure will have an asymmetric blocking capability. They have faster turn-off times and are used for inverter applications. These are the output characteristics of the IGBT. This is non-axis is a VCE and y-axis is a IC. This is transfer characteristics of IGBT, and x-axis is VGE and y-axis is IC. Collector current and the gate emitter voltage. This is the equivalent circuit of the IGBT. Thank you. And the simulation part will be explained by the Veerendr, my friend Veerendr. Thank you.
Hi, this is Veerendr. Now I am going to explain the simulation of the IGBT static characteristics as my friend explained in the PPT. Now I will show you how it is working in simulation in multi-sim. First we will take the IC. We will take the IGBT IC, go to get new part and select transistors. In the transistors select IGBT, and we will take IGBT as 2N6976. we place here. Then we need two DC sources. Go to sources, then select DC power source as keep it here, and one more DC source, keep it here. And we need a resistor. Go to basics and select resistor. Resistor value we take it as 5 kilo ohm and place it here. And we need a ground. Go to sources again and select ground here and place it here. Now close it. Now connect the wires. This is connected to 5 kilo ohm, and this source is VDS, drain to source voltage, and this is connected to ground. Then this one is connected to static characteristics. Is the characteristic as the drain to source current varies with the drain to source voltage, keeping gate voltage constant. Now we change the gate voltage value. We'll keep it 30, and the value we will name it as the VGS. Then we will change the drain to source voltage. This also we will keep it at 30 volts, and this one VDS, name it as VDS. Now go to simulate, select analysis. In that select DC sweep. DC sweep, check the value. Start value will give it as 0 volt, and end value will take it as 25 volt, and increment will give it as 5 volt. And use source 2 again. Start value 0 volt, stop value 25 volt, and increment is 2.5 volt. Now output, will give it as output. Remove this expression and add I versus VDS, add here. Then simulate the experiment. We will get the transfer characteristics as this one. Now we change the direction, then again go to analysis. In that go to DC sweep, and again now output expression we remove it. Now go to add expression, add minus of ID base. Yes. Now simulate it. Now we are getting the DC transfer characteristics. Thank you.